Hello everyone, this is Deepthi and in this video I will be explaining about Project 1 and Project 2 of NAND2TETRIS course. So to begin with, what is this NAND2TETRIS? So this is a course in which we build a computer named Hack by using elementary logic gate NAND. Firstly, we will build all the other logic gates using a NAND gate, and this is exactly what we do in Project 1. Here we first build all the elementary logic gates and their bitwise versions. Here are the names of chips we are going to build. NAND, NOT, AND, OR, XOR, MUX, DMUX, NOT 16 version, and 16 versions of AND, OR, and MUX. And there is this OR 8-way, MUX 4-way 16, MUX 8-way 16, DMUX 4-way, and DMUX 8-way. So what all we need to do this project one? We need a hardware description language, a test description language, and a hardware simulator. So we get a hardware. First, we should go to this NAND2TETRIS website and have to download this software. When you do this, we get a zip file and we extract it. We in this folder. We extract it, we get this folder. When we open this NAND2TETRIS folder, we get two other folders named project and tools. So in tools, we have this many tools, and we just need hardware simulator to do project 1 and 2. So moving on, what is a hardware description language? So it's a programming language used to describe the structure and the behavior of logic circuits. Names and number of inputs, outputs will be given to us. We must write how the chip is implemented in part section. This is a screenshot of a empty HTML file. This file currently does nothing. Here we can see chip and by using this keyword chip, we are letting the simulator know there is a chip by name and we can use this and chip directly for building other chips. And inputs are A and B, output is out, and we have to implement we have to write the code for the chip in the part section. So first, let's directly build our first chip, that is AND gate. So in this gate, if either of the input is low, then the output is also low. If all the inputs are high, then the output will also be high. So this is the truth table for AND gate, and this is how we implement AND gate using two NAND gates. The first NAND gate does what exactly NAND gates do: returns low if both the inputs are high, and returns high if both the inputs are anything else. Then the second NAND gate is configured as a NOT gate to invert the output from the first NAND gate. Let's see the HDL code for this AND gate. Yeah, here we have the HDL code. So we are building a chip and inputs are A and B, output is out. In the first NAND gate, we are performing NAND on the input A and B. In the second NAND gate, we are getting the complement of the obtained output obtained from the first NAND gate. So let's see if this works or not. This is a hardware simulator. We first load the chip. Then we load the script. Then we run the program. Yeah, let's see the output file. We have got the desired output. The output is 1 only when both the inputs are a 1. In all the other cases, the output is 0. If you want to check this, we can use this compare file. Yeah, there is no difference between output and compare. So the code we have written is correct. Moving on to the next step, we have OR gate. So in this case, if either of the input is high, then the output is also high. If all the inputs are low, then the output will also be low. So this is the truth table for OR gate, and this is how we implement OR gate using 3 NAND gates. At first, we invert both the inputs and then give the obtained output as input to the third NAND gate. So let's see the code for OR gate. Here is the code. In the first NAND gate, we are obtaining the complement of A. In the second, we are obtaining the complement of B. And in the third, we are giving the outputs obtained from the first and second NAND gate as an input to a third NAND gate. So let's see if this works or not. Or .html. Now let's load the script. As we can see here, as the program runs, the input a value of input pins keeps on changing. Now let's see the output file. Yeah, we have obtained the right output because the value of output is 0 only when both inputs are 0. We can compare it. Yeah, there is no difference, so the program written is correct. Moving on to the next step, we have NOT gate. This gate performs logic inversion or complementation. Here is the truth table. So this is how we implement a NOT gate using a NAND gate. A NOT gate is obtained by providing same inputs to a NAND gate. Since NAND gate is same as an AND gate followed by a NOT, when we take same input, it works as a NOT gate. Let's see the HDL code. Here, we are just obtaining the inversion. So let's see if this works or not. Let's run the program. Let's see the output file. Yeah, we have obtained the right output. So let's move on to the next chip. We have XOR gate. So this is the gate which gives us the output as truth when odd numbers of inputs are truth. This is the truth table for XOR gate, and we implement XOR gate using 5 NAND gates. We first obtain complement of the inputs separately using 2 NAND gates, and then first input and the complement of second input is fed into the third NAND gate. Complement of first input and second input is fed into another NAND gate. The output obtained by third and fourth NAND gate are input to fifth NAND gate, which gives us the required output. So let's see the code for it. Here we have code for XOR. In the first NAND gate, we are obtaining the complement of V. In the second, we are obtaining the complement of V. In the third NAND gate, we are giving first input and the complement of second. In the fourth, we are giving complement of first input and the second input. So the output obtained by third and fourth is fed into the fifth NAND gate. Let's see if this works or not. Let's run the program. Yeah, let's see the output file. Let's compare. Yeah, there is no difference between output and compare file. So the code we have written is correct. Moving on, we have a multiplexer. A multiplexer is a device that allows one of several analog or digital input signals which are to be selected and transmits the input that is selected into a single medium. Multiplexer is also known as data selector. Here is the truth table for multiplexer, and this is how we implement 2-to-1 multiplex using 3 NAND gates. Let's see the code for multiplexer. Yeah, here we have code for multiplexer. Let's see if this works or not. Let's run the program. See the output file. Let's compare. So we can't see any difference, so the code we have written is correct. Moving on, we have demultiplexer. This is also defined as a circuit that can distribute or deliver multiple outputs from a single input. A demultiplexer can perform as a single input with many output switches. So here is how we implement our demux, or 1 to 2 demux using 5 NAND gates. Let's see the code for it. This is the code for demux. Let's see if this works or not. Let's run the program. Let's see the output file. Let's see the compare file. So we don't have get any difference between the output and compare file. So the code we have written is correct. So then we have multi-bit version. This can operate on multi-bit basis of length 16. Like multi-bit AND performs AND operation to all the 16-bit pairs obtained by two 16-bit inputs. Let's see the code for multi-bit version of AND gate. Here we have code for multi-bit version of AND gate. We can directly use AND gate because we have already built it. So let's see if this works or not. Let's load the script. Let's run the program. The program has run successfully. This is our output file. Let's compare it. So there is no difference between the output and compare file, so the code is correct. Moving down, we have a 16-bit OR. Yeah. So even in here, we are using directly OR gate because we already have OR gate. We can also implement this using a NAND gate, but it's quite tedious. So let's run and see if this works or not. Yeah. Let's see the output file. Let's compare it. So we can't see any difference between the output and compare file, so the code is correct. And then we have not 16. In here we have used NAND gate. So let's see if this works or not. This is our output file and let's compare it. Yeah, so the code is correct. Moving on, we have multi-way variance. In here, we perform the operation on every bit of the input. In multi-way OR, it performs OR on all the bits of the input. So this is the function of multi-way OR. Let's see the code for OR 8-way. This is the code for OR 8-way. Here we are performing OR operation on every bit of the input. In the first OR gate, we performed OR operation on the LST, least significant bit, and the bit next to it. The same way we have performed OR on every bit. Let's see if this works or not. Let's see the output file. Let's compare it. So as we can see here, if all the input bits are 0, then only we can get 0. If any one of the input bit is 1, then we get 1. So yeah, the code we have written is correct. Next we have mux 4-way, and here is a code for mux 4-way 16. Let's see if this code works or not. Let's load the script. Let's load the script. And now let's run the program. This is our output file and this is our compare file. There is no difference between the output and compare file, so the code we have written is correct. And then we have demux 4-way. This is the code for demux 4-way. Let's check this code. Let's load the script. There is no difference between the output and compare file. Let's moving on. We have demux 8-way, just like the demux 4-way. So let's see if this works or not. Let's run the program. Let's see the output file. Let's compare it. Yeah, there is no difference. So the code we have written is correct. So we have built all the chips of the project 1. Moving on, we have project 2. In project 2, we build the set of chips needed for the construction of ALU of our computer hack. So the chips we are going to build is half adder, full adder, add 16, increment 16 ALU. So First, adder. So an adder is a kind of calculator that is used to add two binary numbers. Many computers and other type of processors, adders are used to calculate addresses, similar operations, and table indices in the ALU, and also in other parts of the processor. So this is a circuit diagram of half adder and truth table of half adder. So let's see the code for half adder. Yeah, here we have code for half adder. Let's see if this works or not. Let's run the program. Let's see the output file. Compare. So yeah, the expected output and the obtained output is correct. So the code we have written is correct. Moving on, we have full adder. Full adder can be implemented using two half adders or one XOR 3 and one OR gate. Here we are implementing it using a two half adders. So let's see the code. Yeah, here we have the code for full adder. We have already built the half adder, so we can directly use it. Let's see if this works or not. Slow the script. Output. Yeah, the expected output and the obtained output is same. So the code we have written is correct. Yeah, moving on, we have add 16. This adds two 16-bit numbers. Let's see the code for this. Yeah, so in here we are directly using half adder and full adders because we have already have that. So let's see if this works or not. So on the program. Output file and compare file. So the output and compare files doesn't have any difference. So the program we have written is correct. Moving on, we have increment 16. So it adds constant 1 to a given number. So in here, we have already built add 16, so we can just use that and add 1 to the given input. So that's what we are doing here. Let's see if this code works or not. Let's load the script. Let's run the program. This is our output file and this is our compare file. We can't find any difference, so the code we have written is correct. And then we have ALU. So it is the basic component of every processor. It is implemented using various logic gates, multi-bit and multi-way variants. So now let's see the code for ALU. So this is our ALU. We have used various logic gates here. We have used add 16, mux 16, not 16, or 16 way and not gates. So let's check if this works or not. Slow the script. Yeah, let's see our output file. Let's compare it. Yeah, we can't find any difference. So the code we have written is correct. So we have implemented all the chips. We have built and implemented all the chips of project 1 and project 2. So thanks for watching the video.